Good day. Welcome once again to our mathematics live class for our Jamb online exam. Now, this is very, very important, and these Jamb classes would be part of a series of Jamb classes, not just limited to mathematics, but as well as English, chemistry, biology, economics, and a host of other important and essential subjects that we have in the Jamb curriculum. Today we'll be beginning with our Jamb live class brought to you, of course, by your study part. Make sure you stick around, like the video, invite your friends to also join in the live class as well as we begin a very interesting journey today in the world of mathematics. Now, to begin, let's give ourselves some sense of reminiscing. First off, we understand that in the concept of calculus, we have two broad areas, two broad concepts. The first bit of concept within calculus is the area of differentiation. For differentiation, we can term it as a series of decreasing effects in terms of the power of that particular number or variable, as the case might be. In essence, we say that if you carry out differentiation processes on algebraic functions, for instance, with a general form of ax raised to power n, then we can differentiate this function using the differentiation symbol ddx of ax raised to power n to simply be nax raised to power n minus 1. Now, what exactly is this? What we are simply doing is that as far as the algebraic function is concerned, we pick the power, use the power to multiply the coefficients, and then we subtract 1 from the power. This is why we term differentiation as a decreasing effect on the power on the variable. We move further. Because algebraic functions are not the only kind of functions we can differentiate, we have so many other kinds of functions that we can, of course, carry out differentiations on. A good example of that kind of function is the exponential function. In fact, for the exponential function, we pick a general form e raised to power f of x. So much so that if, now let me write the differential in a different way other than this. If y is equal to e raised to power f of x, then we can say that dy dx in this case, now we are writing the function in terms of calling it a dependent variable y, right? Remember, in this form, y is the dependent variable and then x is the independent variable. Those are very important terms. We term x as the independent variable and we term y as the dependent variable. Y being dependent is the fact that whatever value of y you would have will be completely obtained by that value of x, which is independent. That is just the meaning of the two words. Now, we can differentiate y with respect to x, written as dy dx, or sometimes written as y prime. So you can see it in different forms like this. Now, what would that result be in terms of this exponential function? What the exponential function just simply tells you in simple detail is differentiate the power. Now, when you differentiate the power, that is f of x, it gives you f prime of x. That is the differential of the power f of x. Of course, you can either write it as f prime of x or write it as df dx, as the case might be, just like we have written this. And then once you have differentiated the power, multiplied by the original exponential function. And you would say you are done with your differentiation for this exponential function. Simple, straightforward, direct, straight to the point. Of course, differentiation does not stop there. We can have it for other kinds of functions as well. What if we have it for the logarithmic function? For the logarithmic function, now we'll be talking about concepts like ln f of x. That is the logarithm of f of x. Ln just meaning the natural logarithm or the logarithm to base e. So when you have ln as a function, you are simply talking about the logarithm to base e, right? Where e is, of course, the number approximately 2.718, as the case might be. Now, how do we differentiate this? The differential of this logarithmic function is, in fact, the differential of this inner function, f prime of x, and then divide it all by the function of x. So now, in this case, we are not dividing it by the ln, but we are just dividing it by the inner function itself. This is how we carry out the logarithmic function. Of course, these are just bits and pieces of kinds of functions we can carry out differentiations on. Take a moment, go through all this, and you'll see that these are in fact functions that you are very, very familiar with. Of course, the functions we can differentiate do not end here. In fact, we can differentiate trigonometric functions as well. Now, in this differentiation of the trigonometric functions, we'll be picking several kinds of trigonometric functions that we can differentiate. First off, we can differentiate the sign of a function. Now, when we differentiate the sign of a function, what do? We pick this inner part of the function, differentiate it, then multiply it by the differential of the trig function itself. Now, when we differentiate sine, what do we have? We differentiate sine, we get cos. Very important. This is a standard differential. The differentiation of sine gives us cos. Very, very important to note. So, for example, let's say we are differentiating sine x. This will simply mean that differentiate x, that is 1, differentiate sine, that is cos, and then return the original function. So your final answer will simply be what? Cos x. Simple and straightforward. That was why we say the differential of sine x is cos x without problem. Another kinds of trigonometric function we can have is the cosine. When we differentiate the cos of a function, what do? We simply first and foremost differentiate the function f prime of x, then differentiate the cosine. That gives us minus sine. That's another standard form. When you differentiate the cosine of a function, you have it as minus sine. And then this gives you what? F of x. So your final result will be minus f prime of x sine f of x. Next, we can have the differential of the tangent of a function. When we differentiate the tangent of a function, what do we have? Again, we will first and foremost differentiate the inner function. That is f prime of x. Next, we will differentiate the tangent. And whenever we differentiate the tangent, we will have a secant squared function. So where the SEC simply means secant. And this is very, very essential. Of course, there are different other kinds of trigonometric functions you can have, but these are the three most important functions that you would find yourself using most times and every single time within your calculations. To find out more about our knowledge into differentiation, you can check out more on the concept of differentiation under calculus via our website www.yourstudypad.com. For today's class, our focus will be on the second branch of calculus that we have talked about. We have said that the first branch of calculus is in fact differentiation, and that differentiation can be seen as a process of reduction of powers if you were to define it in terms of the algebraic function. What then would there be the second branch itself? And that second branch is in fact what we refer to as integration. Integration in broad terms is referred to as the reverse process of differentiation. In a minute, we will look in detail as to what we refer to as the integration of function. For now, take a quick look at the various standard functions we have written on the board so far, while we give ourselves a moment to look at this before we now begin the second bit of business, which is in fact our major bit of business for calculus today, which is integration. As we have said, should you want to know more about differentiation, you can visit our website at yourstudypad.com, as well as look at some of our videos which you have earlier done, so that you have a very in-depth knowledge on differentiation. Today, we will begin integration in detail for us. As explained earlier, we can consider the fact that integration is again the reverse process for differentiation, which means that every single process we carry out under differentiation can be completely reversed without having issues when we deal with integration. It doesn't obviously mean that it's going to be a straightforward process of reversal, but it just means that whatever we get from the first stage, we can always get back to that first stage if we use the process of integration. That is what we are going to be focusing today. Now, for integration, we have to first and foremost put forward some preliminary assumptions. First off, how do we integrate? How do we integrate? So let's consider the different kind of functions that we definitely integrate. The first kind, again, just as we considered in the differentiation case, the first kind of function is, of course, the algebraic function. For the algebraic function, how do we carry out this integration? Recall that when we talked about the differentiation method, we talked about a reduction in the power. For the integration case, we will now be looking at an increase in power. How does it work? Let's consider a general form, ax is per n once again. Then, if we integrate, this is the integration symbol, ax is per n dx, which means we are integrating ax is per n with respect to x. Then, how do we carry out that integration? The very first thing you have to note as far as integration is concerned is integration will only concern itself with that independent variable. What does that mean? It means that this constant a can be brought out of the integration symbol. So I can bring it out and have integration of x is per n dx without problem, because a is in fact a constant or a coefficient of x is per n. Now, how do I integrate this? The integration of this is simply an addition to the power of 1 and then a division by the new power. Addition of 1 to the power, division by the new power. Now, once we do this, the next important thing, which is very essential that you must not forget, is in fact to add a constant of integration, plus c. Usually it is written as the letter c. Sometimes it can also be written as the letter k, and so on and so forth. So the integration of ax is per n will simply now be equal to ax is per n plus 1 divided by n plus 1 plus c. And this is a generalized form. Now we can see if we can reverse this process to get ax is per n back. How do we do this? Integration has brought us here. Let's see if differentiation will bring us back. That means if we carry out the differentiation of ax is per n plus 1 divided by n plus 1 plus c, what will happen? Recall that if you were to differentiate this, the rule of differentiation of algebraic functions says multiply the power with the coefficient. So you have n plus 1 multiplied by a, subtract 1 from the power. So if we subtract 1 from the power, we'll be left with n. And of course, we are still divided by n plus 1. Then here you have plus c. You have to differentiate this, right? Differentiation is an additive function. So it differentiates this and then differentiates this as well. So differentiation of c, how do you do this? Do not forget that when you write c, it's still the same thing as saying d dx of cx raised to the power 0, because you know that any non-zero value raised to the power of 0 will in fact give you 0. So it means that if you were to differentiate this, what would you have? You'd have c times 0, x raised to the power 0 minus 1. And this, of course, will make sure you have 0. So that is why we say that the differential of any kind of constant is always 0. So it means that if we differentiate c here, we'll have 0. So this is what we have left. Of course, this n plus 1 will cancel the denominator. So you have ax raised to the power n left without problem. So you see that yes, they are in fact reverse processes of one another. You can try this for any kind of function you have, but this is just to show you that when we say that the integration is a reverse process of differentiation, it follows through literally. This is how we integrate algebraic functions for any kind of algebraic function you can have. Let's see how we can pick different kind of examples to showcase this. Now, let's consider first example. Let's pick something very, very simple. Let's integrate 3x raised to the power 5 dx. Now, this is our function. Remember, the integral is mostly concerned with the variable itself. So we can bring out the constant. So you have 3 integral of x raised to the power 5 dx. And then integrating this, what would we have? We would have 3 into x raised to the power 5 plus 1 divided by 5 plus 1 plus c. And then simplify, you'd have this as 3x raised to the power 6 divided by 6 plus c. And this is in fact 1 over 2 x raised to the power 6 plus c. Simple and straightforward. Why? Because when you have this function in this case, 3 will cancel here to leave 2, which is why we have 1 over 2 here. This is how we can integrate 3x raised to the power 5. Let's take something else. What if in this case we want to integrate 4x raised to the power 8 dx? Again, the same process happens. We bring out the constant. We are left with x raised to the power 8 dx. We add 1 to the power. And then we divide by the new power. And then we add the constant of integration. So we would have 4 over 9 x raised to the power 9 plus c. Now, it is important to note that this constant of integration we are adding is in fact because of the fact that we are integrating in something we call an indefinite bound. These are in fact integrations of indefinite bounds. What does that mean? It means that they are integrations without any limits in terms of the values they can take in. Which means that once you integrate within that indefinite bound, it is always important to assume that yes, there will be some sort of constant that would be formed whenever that integration process is carried out. However, the moment you now begin to integrate within definite bounds, integrations which would look something like this, this means it's integration in definite bounds or definite integrals, then whenever you carry out integrations like this, there is now no need to put in a constant of integration. And the reason is simple. Recall that this is what we refer to as a lower bound, and this is what we refer to as an upper bound, which means that within the concept of the function in which you are integrating here, the value of that function being integrated will never exceed b and will never be lower than a. So a is the lower bound possible and b is the upper bound possible. Of course, that is why whenever we carry out definite integrals like this, we always have f of b minus f of a, where f is in fact the integral already gotten from this point. Some places you see this f written in capital. Of course, within the course of our study into integration, at some point, we would also be talking about the integration of definite bounds. But for now, let us talk about the integration of indefinite bounds to great effect. So, Let's take another example. Let us consider the integral of x cubed plus 1 dx. Now, when we integrate this, what exactly do we do? Now, just as the differential is in fact an additive function, the integral is also an additive function, which means I can split this as the integral of x cubed dx plus integral of 1 dx. And then the integral of x cubed, again, add 1 to the power, divide by the new power, plus, now, because you have splitted the integral, that still does not mean that when you integrate this, you put a plus c, and then you integrate this, you put another plus c. There is no need for that. Why? Because if you were to put a constant here, and then you were to put a constant here, both constants would obviously add up together to still form a constant. So since you know that they will add up to form a new constant, just put one constant at the end, and that will be all. So here, integral of 1. Now, do not forget that 1 is essentially the same thing as x raised to power 0, or 1x raised to power 0. So, if we integrate this, we'll have x raised to power 0 plus 1 divided by 0 plus 1. And then plus c. So what would we have? We'll have 1 over 4 x raised to power 4 plus x plus c as our final result. This is how we carry out the processes of integration. Now, on your own, to ensure that you have been following exactly what we've been doing, let us try to carry out the integral of 6x raised to power 2 dx. We should not spend more than 30 to 1 minute on this, 30 seconds to 60 seconds on this question. It's pretty straightforward. Bring out the constant, add 1 to the power, divide by the new power, add your constant of integration. So let's see exactly what you'd get as your final result when you carry out this process. Take a moment or two to try to solve this question on your own. Of course, this is a mathematics class, so as much as possible, try to have your pen and paper with you so that you'll be able to carry out simple calculations like this, so that you can show that yes, whatever you have learned, you are actually following through with the entire process. Of course, you will find questions of this nature in numerous forms on our website www.yourstudypad.com, as well as our question bank, which is also available there, where you can keep yourself busy and practice as much as you like. Yes, so at this point, I believe you should be able to have gotten a solution for this question. Great, so let's continue. So here again, this is simply just going to bring out the 6x squared dx. So you have this as 6x cubed divided by 3 plus c, which is the same thing as what? 2x raised to power 3 plus c. And that will be all. So this is how we carry out integrations of the algebraic function. Of course, one thing you have to notice is that it doesn't now mean that all algebraic functions will be easy to solve within this kind of straightforward process. No. In fact, you can have instances where you would have to carry out various preliminary processes when trying to integrate functions like this. We would introduce us to as many of those kinds of functions as possible. Now, the first kind of algebraic function we want to draw our attention to is the integration in terms of negative powers. Integration in terms of negative powers. That is, so let's have our example 5 now. That is, what if you want to integrate 1 divided by x cubed dx? Then you would probably say that, okay, this is a fraction. How would I deal with this? There's no problem. You can in fact apply your law of indices to this and write it as a negative power. Then at this point, you can just directly integrate. Add 1 to the power, divide by the new power, plus c. So your final result will be what? Minus 1 over 2, x is power minus 2, plus c. And you can rewrite the x raised to power minus 2 in terms of the fractional form as minus 1 over 2x squared plus c. Of course, it is always good to write it in this form because your question was given to you in fraction form. So it's always very good to also write your variable in fraction form at the end of the day once you have gotten your results. So this is how we integrate negative powers. However, it doesn't mean that all negative powers will follow this process of integration. We will come to see that in a few moments. But first, before we go there, let's consider fractional powers in this case. What if we want to integrate 1 divided by